All right, roll's taken care of. I'm going to ask you guys to pipe down for a moment because I want to talk about some things before we get into the nitty-gritty of class today. All right, so you are all hopefully aware that advising starts next week. Okay. Several of you have asked if you could come advise with me in lieu of advising with your own advisor. How do I put this politely? Stop laughing at me. This is legitimately a serious thing, right? I mean, this is mapping you guys' path out and all of that kind of stuff. I don't necessarily have any problem with that. I'm not saying that to be derogatory towards your advisors or anything like that, but for whatever asinine reason, the College of Engineering and Science has decided to recognize me for the last 2 years in a row as the faculty advisor of the year. I literally do not understand it. But anyway, my only counter argument is that whoever your assigned advisor is will never get any better at doing their job as an advisor if students never go to them. Okay. So I'm willing to compromise and say, hey, if you go to your advisor first and you still have questions or were unsatisfied, you can definitely come and check things out with me. But I would prefer that you went to your advisor first. Is that an unreasonable ask? Okay. I've already got the better part of 100 students on my plate if you only count the people that I'm supposed to be responsible for. I don't know that I have the mental bandwidth to advise the entirety of the 250 electrical engineering students that we have across the entire undergraduate thing. Like, I think that might literally kill me on top of all of the classes that I'm taking. And so I'm just trying to avoid having a nervous breakdown next week. So you're definitely welcome to come ask me questions and this, that, and the other. I'm definitely happy to go over stuff with you, but just give your actual advisor a chance first. If it's not me, before you come talk to me. That's literally all I can ask of you. So anyway, rant about advising over. So today we're going to be talking about resonance in circuits, and we are going to start with the simple case, and I use that term mostly, truly, of a series circuit. Okay, so let's get it popping, as it were. So our next topic over the next several days is resonance in linear circuits. And we are going to start off specifically talking about series resonance. And I want to be clear here. A lot of the material that we're about to cover is, stuff that we've seen before, but we're just thinking about it from a slightly different perspective, okay? So we're going to be looking at series RLC circuits again, which we have looked at extensively in circuits 2 from the viewpoint of what happens when I make a change to this system. That was our transient analysis stuff, right? So way back in circuits 2, we looked at transient analysis for parallel RLC circuits and then series RLC circuits. And then we used the tools that we developed there to figure out how any general RLC circuit would work, or any second order electrical system would behave during a transient condition. And we're going to have a similar approach here. We're going to start by looking at a simple series circuit and examine what resonance means. Then we're going to look at parallel circuits and then put those two things together and be able to kind of get some idea of what happens when we don't have these simple cases. So I'm saying all of that to say, I expect you to already know bits and pieces of this. So it's going to be lighter on the derivation than we would usually do because you've already been exposed to a lot of these things. Okay. So let's consider a simple series RLC network where we have some resistance R connected in series with some inductance L, connected in series with some capacitance C, like so. Going to be looking at this in the frequency domain. So I'm going to choose to represent the voltage drop across this network as some phasor voltage V and the current flowing through this network as some phasor current I, like so. So the input impedance of our network as a function of frequency, so that's Zn as a function of j omega, would simply be the sum of those three impedances, right? So we could write that as R plus j omega L plus 1 over j omega C. And I can kind of clean this up a little bit and express it where we have a distinct real part and a distinct imaginary part as follows, right? So the real part of our impedance should be just the resistance by itself. And then the imaginary part should be some combination of our inductances impedance and our capacitances impedance, okay? So if I factor out the J from this J omega L, that's obviously just going to leave me with an omega L. Nothing particularly wild or crazy there. If I treat this 1 over j omega c as if it were negative j over omega c, which we hopefully all understand that we can do that, because 1 over j is the same thing as a negative j in the numerator, I will have a second term here that looks like negative 1 over omega c. So what value of omega would make the imaginary portion of this impedance 0? You guys should actually already know this, but you could also just set that imaginary part equal to 0 and solve for omega. So tell me what it is. So just as a heads up, omega L minus 1 over omega C is equal to 0. Looks like omega L is equal to 1 over omega C, or omega squared is equal to 1 over LC. So the omega that makes this impedance purely real is square root of 1 over LC. What did we call this in circuits 2? The resonant frequency. That is literally what defines resonance. It is the frequency at which the reactive portion of the impedance completely cancels out or goes to 0. Okay. So this network's impedance will be purely real at omega is equal to the square root of 1 over LC, which we're going to call omega naught the resonant frequency. So what does it mean that the reactance term here has gone to 0 in terms of what the voltage and the current are doing? Okay. So if the reactance term has gone to 0, then that means that the voltage and the current are completely in phase, right? So if my impedance is just R plus J0, the phase angle of the current and the phase angle of the voltage literally have to be the same thing. So that is one consequence of exciting our circuit at resonance, okay? at that particular frequency, what would the power factor of this network, if we're treating it as a load, be? 1. So at resonance, we are delivering the maximum amount of average power we possibly could. So that's another thing to think about in terms of resonance. So what I'm about to draw is a frequency response plot, effectively, for our input impedance for this network. I'm going to look at the magnitude and I'm going to look at the phase angle. Okay. So over here on the left, let's do our magnitude plot. So we're going to have something that looks like this. So this is the magnitude of Zn as a function of omega on the vertical axis and omega on the horizontal axis. Okay. So I'm going to put omega naught right here, and I'm going to put R right here by itself. So we know that at our resonant frequency, the impedance of our network is simply R. Okay? So let's think about what's going on as we allow our frequency to change. Okay? So if omega is very small, what happens to our reactance term? Okay? Well, the impedance of the inductor is going to be effectively 0. Okay? But the impedance of the capacitor is going to be very large. So if we took the magnitude of this thing, we could say that at very low frequencies, the impedance of the capacitance is dominant. Okay? So we're going to start off with a very high impedance for low frequencies. So it might look something like this. Where as we get closer and closer to our resonant frequency, these two guys are balancing each other out more and more and more, and so that we only have resistance at exactly the resonant frequency. As our frequency gets very, very high, the impedance of our inductor starts to become dominant, right? Because 1 over omega c is going to look smaller and smaller and smaller as omega increases. So on the right-hand side of this graph, we should see another curve representing the inductance becoming more and more dominant. Okay. So something like this. And I'm just going to make a note over here on the left-hand side. We have C as dominant. And over here on the right-hand side, we have L as the dominant contributor to our impedance. So at our resonant frequency, then, we can see that the input impedance is at its absolute minimum. Okay? So for any given voltage signal V, our current will actually be at its maximum when we excite this circuit at resonance. If we look at our phase angle as a function of frequency, that graph is going to look something like this. So here's the angle of our impedance as a function of frequency. Here is our frequency, and let's put omega naught right here. Okay. I'm going to put negative 90 degrees down here and positive 90 degrees up here. So if below our resonant frequency, our capacitance is dominant, then what would our phase angle look like? So it's going to start at negative 90 degrees because that's the phase angle of the impedance of a capacitor. And as we increase in frequency, that's going to trend up until we hit our resonant frequency, at which point our phase angle has to be zero because our voltage and current are exactly in phase. And as we go beyond our resonant frequency, it's going to continue approaching positive 90 degrees until the impedance of the inductor is so much larger than the resistor that it just stays there. So we should have something that looks roughly like this for our phase response of our series resonant circuit. So what I want us to look at now is what's going on with the energy in our system. Because this is both really interesting and potentially rather scary. So let's say that I have the following circuit. So let me just write this down as energy relationships real quick. So I have a circuit where I have some sinusoidal source voltage like so, and it is being used to excite a simple series RLC circuit. And I want to look at the energy in my capacitor and my inductor. And let's say Vs of t is simply Vm, so some magnitude cosine of omega naught t volts. So we are explicitly exciting this system at the resonant frequency of the circuit. So what's the energy stored by an inductor? 1/2 Li squared. What's the energy stored by a capacitor? 1/2 CV squared, and all of that kind of good stuff. So we're going to use some frequency domain circuit analysis techniques, just good old circuits one stuff, in order to figure out what our phasor current and our phasor voltage are so that we can use those values and plug it into our expressions. So in the frequency domain, our circuit looks like this. So we would have a phasor source voltage of Vm angle 0 degrees volts. Our resistor obviously is still just a resistor. Our inductor will have an impedance of J omega naught L. Our capacitor will have an impedance of 1 over J omega naught C. And then here is our phasor capacitive voltage, or capacitor voltage. Here is our phasor inductor current, IL, like so. So what will our phasor current be at resonance? So when we're exciting this thing at its resonant frequency. What was that? Yeah. With an angle of 0 degrees. Exactly right. Because at the resonant frequency, we know that these two reactances exactly cancel each other out. So we don't really need to do any circuit analysis at all. If these guys cancel each other out, they're just treated like a short circuit. Okay. So we would have IL is equal to VM angle 0 degrees over R. Absolutely right. What's our capacitor voltage going to be? So I think we can just use Ohm's law because we know the current flowing through the capacitor, we just found it, multiply it by the impedance of the capacitor, and we get the voltage drop across our capacitor. So that would give us, so let's do that really quickly. So VM angle 0 degrees over R times, so let's do this as 1 over omega naught C with an angle of minus 90 degrees. Everybody okay with me expressing my capacitor impedance like this? Right? So this allows us to write this as simply Vm over omega naught RC with an angle of negative 90 degrees. So the energy stored by my inductor is 1/2 L times my inductor current as a function of time squared. Okay. So that would be 1/2 L multiplied by, so how am I going to convert this back into the time domain? Well, the magnitude of my current would be Vm over R cosine omega naught T with a phase angle of 0. Right? Squared like so. And this looks like, so I'll have a Vm squared in my numerator. I have an L in my numerator. And then I have a 2R squared in my denominator. Cosine squared omega naught T. Units of this whole thing will be in joules. Are we okay with this? What about my capacitor? So 1/2 C times the voltage drop across my capacitor squared is going to look like 1/2 C times Vm over omega naught RC. So notice here that I have a phase angle of negative 90 degrees. So I would have cosine of negative 90 degrees, which is the same as sine with 0 phase angle. And so this is going to give me Vm squared over twice omega naught squared R squared times C times sine squared of omega naught T joules. Now, What's omega naught squared again? So omega naught squared is 1 over LC. So if I have an omega naught squared in my denominator here, that's the same thing as having an LC in my numerator, right? So I'd have an L in my numerator and then the C in my numerator would cancel the C in the denominator. And what would I have left? This guy right here times sine squared. So I'm going to make a note of the substitution that I'm doing here so that you guys can follow along. Omega naught squared is equal to 1 over LC. And so by substituting that in, we wind up getting Vm squared L over twice R squared sine squared omega naught t. So if I were to plot these two energy functions as a function of time, it would look something like this. So I'm going to do the inductor energy in red. It's a cosine function, so it's going to start at its maximum value. So something approximately like this over this particular time interval. And I'm going to do the capacitor energy in blue. So we're going to have a sine squared thing. So it's going to effectively look like the exact same thing, but it's just going to be inverted. In green, I'm going to add these guys together. What do you think it's going to look like? Straight line. The straight line. Exactly right. Where this peak value is Vm squared L over twice R squared. So effectively what we have happening at resonance specifically is our inductor is just dumping energy into our capacitor until our capacitor starts dumping energy into the inductor for the next half cycle, and that happens over and over and over again. So we just have what's typically called an LC tank or a resonator. Yes.
I have a question. I guess since the sine and the cosine squared, are your peaks happening at half your time period that they would normally happen?
They aren't happening at the halves. So let me answer Isaiah's question because I believe I understand what it is, right? So if we had a sine function or a cosine function by itself, not squared, it would be oscillating between its peak value and negative its peak value, right? So just as a quick aside thing here, I'm going to wind up erasing this in a moment. There's literally no reason to write it down. So cosine squared of x is the same thing as 1/2 plus 1/2 cosine of 2x, right? And if I'm remembering correctly, and tell me if I'm not, sine squared x is the same thing as 1/2 minus 1/2 cosine 2x. So at 0, we have 1/2 plus 1/2, and then, which is why we're at its maximum value here. And at 0, we're at 1/2 minus 1/2, which is why we're at our minimum value of 0 here. So these squared signals should never dip below the horizontal axis. They are oscillating between their peak value and 0, and they have a DC offset of exactly 1/2 of their peak value. Did that answer your question? Okay. Like I said, I know 100% for sure that my cosine squared thing is right because I've used that in front of you guys at least a dozen times at this point. I'm 98% sure that I'm remembering the sine squared thing from memory correctly. And it has to work that way, or this doesn't make any sense for what it's worth. All right. So we have this system that is just constantly passing energy back and forth, back and forth, back and forth between the energy storage elements. At resonance, that's all that's going on, right? Excuse me. So let's define some things, okay? So capital W subscript D. So this is representing the energy dissipated in our system per cycle. Another way to think about this is literally just what's the resistor do? Because it's the only thing that's not transferring energy back and forth. It's still, there's a current passing through the resistor, right? So it is converting electrical energy into heat with every single cycle. That is for sure happening. So this WD is just the energy absorbed by the resistor per cycle, okay? And that's important. So we're going to determine this by taking the integral of the power absorbed by the resistor as a function of time. And we are going to integrate over exactly one cycle. Makes sense? We know that the integral of power is energy. And if we integrate over exactly one period or one cycle, then this gives us our energy dissipated per cycle. Well, this is nothing more than the integral from 0 to t of our resistance value times our inductor current squared, because that inductor current is passing through the resistor, and we know that the power absorbed by a resistor can be expressed as I squared times R. So nothing particularly fancy there. Let's substitute in our time domain expression for our inductor current. So we'll have R times Vm over R cosine omega naught t squared dt. Let's take this one step further here. So I've got my R, and then using literally that identity I just wrote down a moment ago, cosine squared is 1/2 plus 1/2 cosine of 2x. We're going to have Vm over twice R plus Vm over twice R cosine of twice omega naught t dt. So what happens when I integrate this guy right here, the cosine function, from 0 to capital T. So just to clarify here, capital T represents the amount of time it took for our cosine of omega naught signal to go through exactly one cycle. So it represents the amount of time it will take this guy to pass through exactly 2 cycles, because this is twice the angular frequency, right? So what happens when I integrate a cosine function or a sine function, literally any sinusoid, over an integer number of periods? It's 0. I've been harassing you guys about this since literally circuits 1. It's been 0 the whole time. It's still 0. This whole right-hand term goes away. Yes. Yeah, I think you're right. Yes, you're definitely right. Thank you for that. Okay. So, thank you for catching that. Ethan? I think it's Ethan, right? Ethan Ice, right? Okay, just making sure I'm not having a stroke. I don't smell toast or anything for what it's worth. So this R here is going to cancel the squared here, and we're going to have simply VM squared divided by 2R times our period. Well, we know that we can express our period in terms of our angular frequency, again, from circuits 1 relationships, right? So just to recap that, we know that omega is 2 pi f, which is the same thing as 2 pi over capital T. So that means T is just 2 pi over omega. In general, we're using omega naught for that specific frequency here. And so that's going to give us 2 pi times the magnitude of our voltage squared divided by twice omega naught times R. And I'm leaving it like that form intentionally. I know the twos can cancel out, but I don't want to just yet. Yep, okay. Everything looks hunky-dory to me. So we're going to define something new here. Okay? We're going to define what's called the quality factor of our system. So the quality factor Q of a resonant system is defined as 2 pi times the energy stored in the system divided by the energy dissipated per cycle. So this quality factor is just a figure of merit that is used to describe effectively resonators, anything that resonates. So we can use quality factor to describe resonant circuits. We can use quality factor to describe mechanical systems that are resonating. And effectively, what the quality factor tells us is, let me frame it in a slightly different way. This is a quick aside, but it's relating back to things that we've done in the last couple of days. Okay. So if this is my transfer function for a system, measured in decibels, and here's my resonant frequency. Right? So when I have a complex conjugate pole, we found out that depending on what our damping factor was, we might see a little bump here, right? The higher this bump is, the higher our quality factor for our system is. So quality factor and damping factor are inversely proportional to each other. So this is just another way that's kind of telling us effectively, the higher my quality factor is, the easier it is to excite my system at its resonant frequency. Or a better way to put it would be, the higher my output amplitude of my signal will be at the resonant frequency. So think about it in terms of a mechanical system really quickly, okay? So if we have a situation where our mechanical system had a transfer function that had a complex conjugate pole, and its quality factor was very high, effectively it would take only a small amount of energy to create a large change in displacement in that system, meaning that it's potentially unstable, right? So a small amount of energy goes in, gives us a very large response at the output. That's what the quality factor is effectively telling us. In mechanical systems, that can be incredibly bad because we can cause a structure to collapse. In electrical systems, it's usually pretty good because it means we can take a very weak signal like what we're picking up by an antenna and boost it to something that can be used by our amplifier so that we can hear the signal. Okay, so it's all related to those same concepts that we've talked about previously. All right. So going back up here, this is simply 2 pi times our stored energy. So what's our stored energy? This guy right here. It's constant because it's just the sum of the energy stored by the inductor plus the energy stored by the capacitor, which will be a constant value of Vm squared L over twice R squared. Our energy dissipated is just this guy right here. So I'll have 2 pi times Vm squared over twice omega naught R. So let's look at some things really quickly. This 2 pi cancels that 2 pi, very obviously. Vm squared cancels Vm squared. I've got a 2 there and there. The R squared here, one of those R's gets canceled by the R in the denominator of the denominator. And all that's left behind is effectively omega naught L divided by R, or 1 over R times the square root of L over C. So this is our quality factor for a simple series resonant circuit. So we can now, if we have a particular quality factor in mind, let's say we were trying to design a receiver We know what the impact of the different resistor values we use, the inductor values we use, and the capacitor values we use have on trying to set or establish a particular quality factor for that system. Another way that we can look at this thing potentially. So this is just a quick aside. So we have omega naught L over R would be 1 over the square root of LC times L over R is L over R times the square root of LC. So L over the square root of L looks like a square root of L in the numerator over R times square root of C. And I'm going to multiply by square root of C over square root of C. And that gives me square root of LC divided by RC, or 1 over omega naught RC. Just a different way to put it in context. They're all equal to each other, but we could do omega naught L over R has to be the same thing as 1 over omega naught RC. What's kind of interesting to me is this is literally omega naught times the time constant of an RL circuit. And this is 1 over omega naught times 1 over the time constant of an RC circuit. Again, everything that we've done before always comes back and shows up in interesting ways. All right, so the last thing that I want to do for today, I believe, is analyze a circuit. And I want us to make some observations about what's going on. Okay. So let's say that we have a simple RLC circuit, and let's throw some numbers in here finally, right? So let's say that we have a 3 ohm resistor, a 0.1 Henry inductance, and some unknown capacitance C that we'll be dealing with in a moment. Here is IL of t. Here's VC of t. And Vs of t is 10 cosine 1800 t volts. I want us to determine A, what value of C will place the circuit in resonance. B, what is Q using this value of C? And C, what are the magnitudes of the voltage drops across L and C at resonance. So let's start with the easy part. A, what value of C is going to place the circuit in resonance? So we can either use this guy right here because we know L and R, but I think this guy right here is probably easiest because we also know simply omega naught and R directly, so we don't have to do any other, actually, no, sorry, this is a quality factor thing. Sorry, I'm just having a complete and utter brain fart. Resonant frequency is just the square root of 1 over LC. We have enough information regardless. We don't have to think about anything. My bad for just completely forgetting what the hell I'm doing. So omega naught is the square root of 1 over LC. C is then 1 over omega naught squared times L. So this is 1 over 1800 radians per second squared times 0.1 henries. And this comes out to be 3.086 microfarads. Sorry for the brain fart. Does that process make sense to everybody? Hopefully pretty damn straightforward. Okay, now that we know our value of C, we could figure out our quality factor. Actually, we didn't even need that C value for that anyway. Our quality factor Q could be given by omega naught L over R. So that would be 1800 radians per second times 0.1 henries divided by 3 ohms. So we would have a quality factor of 60. Quality factor is a dimensionless quantity for what it's worth. Here's where things get fairly interesting. Okay. So ultimately here, I want to figure out what the value or the magnitude of the voltage drop across my capacitor is and the magnitude of the voltage drop across my inductor is. We could convert this circuit into the frequency domain and all of that kind of stuff, but this is a simple enough circuit where we don't necessarily need to, right? So if this circuit is oscillating at resonance, the impedance of the inductor and the impedance of the capacitor cancel each other. So the inductor current IL as a phasor, we can see pretty easily, is just going to be our voltage source voltage as a phasor. So that's 10 angle 0 degrees volts divided by our resistor value of 3 ohms is just 10 thirds with an angle of 0 degrees amps. Are we all okay with that? How would we find the magnitude of the voltage drop across our capacitor? Ohm's law, right? So it would just be the magnitude of our currents multiplied by the magnitude of our impedance, right? Phase angle doesn't matter. So that would be the magnitude of I divided by omega naught C. So that's 10 thirds of an amp over 1800 radians per second times that 3.086 microfarads, which comes out to be 600 volts. For the magnitude of the voltage drop across our inductor, that's just going to be the magnitude of our current times the magnitude of our impedance of our inductor, omega naught L. So that is 10 thirds of an amp times 1800 radians per second times 0.1 henries also comes out to be 600 volts. Anything seem weird to you guys? So we have an input voltage of 10 volts, right? Sinusoidally oscillating between positive 10 and negative 10. The voltage drop across our capacitor and the voltage drop across our inductor have a magnitude of 600 volts. They are 180 degrees out of phase with each other. So when one is at positive 600 volts, the other one is at negative 600 volts, but still, that is a pretty damn big voltage drop being applied across those elements. Is that problematic? Well, it depends on the ratings of those particular components in your circuit, right? So if you are going to drive a circuit at its resonant frequency, the whole point of driving a circuit at a resonant frequency from an electrical engineering standpoint is to get the largest possible response due to the smallest possible input. We are seeing that right here. We are effectively, in some way, shape, or form, getting what looks like a huge degree of amplification of our input signal if we were taking our output voltage in this system to be the voltage drop across either our capacitor or our inductor. So we better make damn sure that it's rated to be able to handle a 600 volt AC signal, or we're going to burn it out. If you went and did this in the lab with just an off-the-shelf capacitor, you're going to get half a cycle before that capacitor literally just burns out, because you're just trying to dump way too much energy into it because you're exciting it at resonance. So when you're designing circuits for resonance, you have to expect these kind of things and plan accordingly so that your system is robust enough to be able to handle it. Because we're at a point where the energy transfer is at its maximum. Yes.
So if you're actually designing, do you have like a factor of safety or something?
Absolutely. So if you look at a data sheet for any capacitor, you'll see that they're rated for specific voltage, right? So if you go by the small thin film capacitors like we use, they're typically probably rated for somewhere in the ballpark of like 25 volts AC, or 25 volts RMS or something like that. You can buy more robust capacitors. Definitely, all that's going to do is probably have a different dielectric material in them so that it doesn't break down as easily so that you don't burn them out. For what it's worth, when you're looking at inductors, they're going to have a rated current because you can't have too much current flowing through it or it'll burn those guys out. So the 10/3 of an amp flowing through that inductor probably isn't an issue. The 600 volts across just any random old capacitor is probably going to be an issue. For what it's worth, the resistor will be probably totally fine. Well, actually, I say that 10/3 of an amp. So 10/3 of an amp. Let me grab a calculator here. Just seeing how much power is being absorbed by the resistor. So 10/3 of an amp squared times 3. So it's dissipating 33.3 watts, which that's a whole heck of a lot for a resistor as well, for what it's worth. Yeah. All right, I think this is a good stopping point for today. So we will look at this a little bit more in the context of frequency response at the beginning of our next class meeting. I'm hesitating here because we're actually way ahead of where we need to be, or at least where I was last year. I'm considering making next Monday just a review session for the exam. It looks like a lot of people are giving me a thumbs up about that. So let's review on Monday for the exam on Wednesday, and then next Friday we'll pick back up on resonance.